Good afternoon, I am Mr. X. Thank you for joining me for this video. You remember very well that very recently I presented a video on approximate integration where we talked about the midpoint rule. These techniques of approximate integration are important, especially for those instances where you have a novel function for which some sort of a derivative, antiderivative, or integral template is not available. You have a experiment data and all of that, and you have to be able to integrate it, and you don't know how to do it, then you have to do approximate integration. If you're looking here at this specific video on trapezoidal rule, it's important to take a little bit of a time and see how this trapezoidal rule comes about, because based on the midpoint rule or compared to the midpoint rule, this is a little bit more complex. If you have a representation here for a specific function a to b, I have two instances over here because you have to consider the left endpoints and the right endpoints with regards to the rectangle that you will draw inside. You know, when you're drawing a rectangle with regards to a curve, this Riemann rectangle has a left endpoint right here, a right endpoint, and a midpoint. We're not looking at the midpoint, but we're looking here and here. Based on how the curve touches this rectangle, you can either have left endpoints and right endpoints. If you're drawing your, let's say for this specific instance, we're looking here at n equals 3, so we're drawing 3 rectangles. If you're looking at rectangles here where the left point touches the curve, then you're going to see something like this. The left point is touching the curve and we have to fit in 3 triangles. You're seeing that to be the case. The left corner of each rectangle is touching this curve. With regards to the right endpoint, now only the right side of the rectangle must touch the curve, and your curve will be something like this. Again, we're drawing only 3 because we're learning here how the procedure is done. Of course, there are some inaccuracies here, but I'm trying my best to be a little accurate. But you see left endpoint, right endpoint. Well, now put that aside and remember this, that the trapezoidal rule with regards to the intervals that you have, they represent, or this rule represents, an average of your values for the left and right endpoint approximations. Now let me start adding some intervals over here because I want to show you how the formula develops. We know this is right endpoint, we know here this is left endpoint. If we have a certain x0 here, x1, x2, x3, likewise here we have a x0, x1, x2, x3. Because we have an n value here of 3, we know exactly where we go up to. Otherwise we'd be looking at the very end at something which is xn, and right before it you'd be looking at x and n minus 1, the value right before, and then at the very beginning you'd be looking at x0, and then you'd have all of these other values in between. I'm just trying to eliminate using these type of terminology because I don't want anyone to get confused, and I want to keep things more practical. But you see this right here would be my x3, this would be my x2, that would be x0, and I'd have a x1 in between. Setting that aside, now let's look. When you're looking at this specifically, you still have to worry about a delta x, which is your b minus a divided by n. In this instance, we know all of that, and we're looking at something which looks like this in terms of a function for which no template is available. There's no means of integrating, so we've decided to use trapezoidal rule, and we've decided to use approximate integration. Now remember, for each interval, left endpoints and right endpoints, the trapezoidal rule is bringing in the average of those. So your formula will play out like this. You'll have a delta x sitting outside, which is your width of interval. Now for this first interval, x0 and x1, looking for both the left and the right endpoints, you have to bring in their average. So you'll do the x0 value into your function, you'll do the x1 value into the function, and you'll average it out. That'll be the result of your first interval right here, feeding in. Now in your next interval, we're x1 to x2. You have to do the exact same procedure, but we still have to write it out for you, as you can see, and again it's the average of that. F of x1 plus f of x2 divided by 2, and we're not done because we still have one more interval to look at, the x2 to x3, and again left endpoint, right endpoints are being averaged. Here you're seeing an f of x2 plus f of x3 all over 2, and now your formula, the trapezoidal rule formula, has closed because we've gone through it all. When you're looking at all of this, a commonality is present, which is a 1 over 2. That 1 over 2 can be isolated and pushed outside, because you can bring 1 over 2, 1 over 2, 1 over 2. And then what you have left in between is this, f of x0. Once you open up all of these parentheses, everything is in a plus format. You can just easily open up everything. And this is what you see. And I'm going to write it out here for you without missing out on anything. See what we have. We have f of x0, we have 2 f of x1s, 2 f of x2s, and 1 f of x3, because we actually have that. But when you combine these, this f of x1, there are two of those, you can combine them. And let me erase a few things over here and combine them for you. We end up having a 2f of x1. We have 2f of x2s. So let me erase it. Erase one of these and bring it. And I have a 2f of x2. But you see how everything is shaped out. Now I'll just put the formula over here in a clean way. The trapezoidal formula will be this. You have a f of x0 plus 2 of f of x1. But this formula is for this depiction over here where n equals 3. Plus 2 of f of x2 plus f of x3, and your formula closes, your template closes. So let's clean this out a little bit over here. But you see what's turning up over here? Your interval has now n over 2, x delta x over 2. You have a first term over here, f of x0. You have a last term over here, f of x3, which is synonymous with your f of x0 and f of xn. These have a coefficient of 1, but anything in between in terms of interval values has a coefficient of 2, and you've seen how that came about. So remember, that formula is exactly as you're seeing it. You're going to have an interval value come in, but it'll be divided by 2. You'll have your very first interval value, and it'll be coefficient of 1. You'll have a very last value, it'll have a coefficient of 1, but all the values you put in between will always have a coefficient of 2. And check this other thing out. You have n equals 3, right? But look, you have 1, 2, 3, 4 items coming in here. 4 terms are coming in here. So you're always going to be thinking about a certain n plus 1 number of terms, which will come into your parentheses here for your trapezoidal rule. So if there's any confusion as to what these represent, it's not hard. Everything is labeled for you. F of x0 is exactly this first value, which is shared among both right and left endpoints right here. Then x1 obviously is the values you're seeing over here, x1, x2, and then x3 right over here. You can always do it like there's f of x0 and then x1, x2, x3. These values can come right through. But there's nothing wrong with what I'm showing you over here, but you just have to remember the peculiarities that have come about in this formula. Let me present an example for you in terms of all of this, and we can show you how that will play about. We'll look at a basic good function for which a derivative, antiderivative, and integral template is all available, something like that, where we have abilities to do everything the normal traditional way, so we can check our answer. And there's nothing wrong if we do this again, 1 to 2, 1 over x dx. Here's my function. Now keep in mind we're looking at everything over here, and let's do n is equal to 4. You don't have to do a long and drawn out table when you're doing the trapezoidal rule, because the rule is already slightly complex to begin with. But this is what we can do. We can determine our delta x is equal to b minus a over 4, which is a 1 over 4. Now look, this is what we can do here with regards to our intervals. You know you're starting from a 1 and you're going to a 1.25 because you're going by quarters. Then you're going from 1.25 to 1.50. Then you're going from 1.50 to 1.75. And then you're going 1.75, you're going up to 2. This right here will be your x0 value. This here will be your x to the n, the last value, which you can say x to the 4. And these values right over here will be all your intermediate values. When you're looking here at the very first value, look right here, everything is falling well into play. You have a 0.25, let's just write it 0.25. You have a 0.25 over 2, which is your delta x over 2. F of x0, this right here is my first term. I'm going to do 1 over 1 because my function is a 1 over x, 1 over 1 plus 2 times f of x1. This is my x1, this here is my x2, this here is my x3, which is also synonymous with x of n minus 1 because it's the term right before the second last term. Now f of x0, f of x1 here is 1 over 1.25, then 2 times x2, 1 over 1.5 plus 2 times this 1 over 1.75. Remember, in all instances our function is 1 over x, so hence we're saying 1 over plus your last term is f of x4, not x3 but x4 is just here a 1 over 2. But you see the coefficient 2 appeared here in the in between terms. The terminal terms have a coefficient of 1. You just have to evaluate all of that with regards to your calculator, and we can do it. We'll bring the calculator here and we'll do all of this here in one single step. We'll work on this part first and we'll do this at the end. We'll look at the first term. It's a 1 plus 2 divided by 1.25 plus 2 divided by 1.5 plus 2 divided by 1.75 plus that right last term 0.5 multiplied by 0.25 divided by 2, we get here 0.69702, which I want to write for you here, 0.69702. Now if you do this in the traditional format, you have basically a natural log x antiderivative from 2 to 1. You know you're doing natural log 2 minus natural log of 1. This is a 0. You're having a natural log of 2. When you do natural log of 2, you have a 0.693. But when you're looking at these numbers, this and this, you're clearly seeing that this number is higher, is larger than this number over here. The actual value is less. If you take this 0.69702 or approximated value 0.69702, you minus natural log 2 from it, you get here 0.003872. And I'll put that value for you here, a positive 0.0038728. What does this value mean? This is your error amount, by how much you've overestimated. Keep in mind with this trapezoidal rule, normally you'll end up with approximated values which are higher or larger than the true values. The midpoint rule will normally present you values which are generally less than the actual values. But in terms of the margin of error, it's still quite negligible and it's quite close to the actual value. So that's all I want to present you in this video, because I wanted to keep this a little more practical and show you how the formula comes about, because this formula right over here, which here is a more of a practically formulated formula for you, tends to be a confusing point for students. But I showed you how that came about and the peculiarities. Your terminal values here have a coefficient of 1. Every value in between has a coefficient of 2. If you have a n equals 4 or n equals whatever, it's always an extra term. Here we had an n equals 4, we had 1, 2, 3, 4, 5 values which came in. So it's always an n plus 1 with regards to the items you'll see in your parentheses, and then your interval divided by 2, because that average came out, it was isolated and brought along with your interval. But if there are any questions with this specific technique, you can always leave them in the comment section and I'll get back to you. Thank you for watching. Have a nice day.